Welcome one more time to the world of resonance and aromaticity. I just want to do a great big picture and kind of go over some of the highlights because it feels like we haven't talked about resonance in forever, and yet it's such an important thing. And how does it tie to aromaticity? All right, so the big tie together, resonance and aromaticity. And I'm kind of looking back through the handout here, but I won't scroll through it. All right, what do we need to remember about resonance? Well, of course, you have to be able to do resonance structures. Yes. So the term conjugated has become very important. Remember, when I say conjugated, it means they all have p orbitals. So adjacent p orbitals. All right. Next, do not forget the allyl systems. So that is a species next to a double bond. I guess technically it could be a negative too. So being one away from a double bond has a very special place. Don't forget when you do have these lone pairs or ions, lone pairs or ions next to a p orbital. Okay, that's another way of talking about these two. Let me see. Oh, and then double bonds with heteroatoms. Remember, for me, that is a built-in leaving group. All right, so just some generics about resonance. Don't forget. Oh, only move. Gonna put this one in red. Only move electrons. Okay, this is not rearrangements. Only move your electrons. All right. They only exist on paper. They're not in equilibrium. They're not isomers. Oh, that's probably a good one to put. They're not isomers, nor are they in equilibrium with each other. Mm, just not a lot of things I really need to highlight. Last but not least, for resonance, is look for stability. Not all of the structures are equal. And don't forget alkenes or double bond systems. And what I mean by that, okay, both of those are allyl, but this one also has a trans alkene. So when you do have double bonds in there and it can possibly make a difference on its substitution, make sure that you don't forget about that. Okay, so just a note about resonance. Do you have to be able to draw every resonance structure in the world? Absolutely not. Do you need to be able to see that there are different resonance structures? Yes. But most importantly, you need to be able to look at a couple possibilities and determine which one is the most stable. Okay, so that's really the drive behind that resonance area. All right. After resonance, we talked about benzene. Now, when we were first learning about functional groups, we learned that benzene was in a world all by itself, and it was called an aromatic compound. And now you know what aromatic means. Now, originally, aromatic did mean, its odor. And for the most part, whether we like the smell or not, they have very distinct odors. And so that's where aromatic came from. And for a while, it was thought that you had to have this beautiful aromatic hextet in order to have those properties. And that is also not true, but those were the molecules that we saw at first. So, like wintergreen and vanillin and those really nice smelling molecules, they all were found to have the hextet. So that's where that idea came from. All right. Then, what about stability? That's really the driving factor here. Aromatic compounds are more stable than expected. Now, I don't think I drew this for you earlier, but it's worth a quick draw. So if you take cyclohexene and you hydrogenate it all the way down to cyclohexane, well, that takes a specific amount of energy. And just according to the textbook I'm staring at, that is a negative 28.6. Wow, this book is old. Kcals per mole. Okay. All right. Doesn't really tell me anything. But what if I wanted to do three double bonds? Okay. Because really for benzene, I need to be talking about three double bonds. So I'm going to have to draw, let me see, 1, 2, 3, 4, 5. I see. One. And I can't make it benzene. And of course, it would take three hydrogens or three molar equivalents. And that one is, and I know this picture is really ugly. That's not benzene. And now, how about benzene? Jolly, those look the same. I know they do, because I'm a poor drawer. The only reason I'm putting that in there is some evidence, okay? There's actual thermodynamic evidence that this extra lowering of energy from an aromatic system is called resonance energy. And there's a fun lab, if you have the program for it, is you can actually go and plug these different molecules in, and it will tell you how much energy you get from hydrogenation. And then you can model, oh, so this is how much energy it takes for each double bond. And you will find that this one doesn't come up with just predicted numbers, and that difference would be called the resonance energy. All right, so we have this new world called aromatics. What are we going to do with those aromatics? Well, we have to understand what they are. And so we decided that we're going to put it into four categories. It has to be cyclic. It has to be conjugated, or nope, it has to be planar. Planar and conjugated usually go together. It has to be conjugated. And it has to have this special number of Hugel electrons. All right. See, I already drew some pictures. See if it'll let me open it. And I'm going to stop sharing and go back in just to make sure you can see it. All right. What kind of aromatics are we talking about? Now, first, I mentioned vanillin and wintergreen. If you will notice, both of these have your benzene rings. Okay, so that's why they thought that aromatic hextet. But these are very nice smelling, at least in my world. I also want to point out, oh, those are phenols. Okay, so those were the nice smelling ones that we started out with. And so benzene was kind of taken to be the parent, I guess, of the aromatic world. And then that is why they're called aromatic hydrocarbons. So that's where the name comes from. Aromatic hydrocarbons. And some that you are familiar with or you will see in the lab, if there is one methyl group attached to benzene, it's called toluene, which we use it as a cleaning solvent. If there are two methyl groups attached and they're ortho to each other, okay, this special family is called the xylene family. If you've smelled model glue, you have this very unique pungent smell. And so we have orthoxylene, metaxylene, and paraxylene. Can you fuse rings together? Absolutely. Okay, so we've got our naphthalene, very interesting smelling. Okay, so this we would be called fused. Well, what if they're not fused together? Okay, now we saw that sometimes that'll mess up your planar and your conjugated systems, but these, okay, they're not fused. They are just connected together. And we've also used that one in lab. It's called biphenyl. Can you have more than just one ring? You bet. Okay, so anthracene and phenanthracene, they're a whole bunch of benzene rings in different orientations. All right, now I keep using benzene rings over and over and over. Does it have to be benzene rings? And the answer is no, it does not. We talked about the annulenes. I didn't leave myself space here. I'll draw it right here. Wow, that is so ugly. Just want to point out, don't forget. Do, opposite, 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 opposite. Okay, that one is not fused, and so it puckers. So don't forget to look for things like that. Well, what about ions? Okay, so we talked about ions. And can it become ionic and achieve the aromatic state? Yes, and this one happens to be the cyclopentadiene radical. Well, what if it has hetero atoms? And the answer is yes, but watch out for where the lone pair lives. Is it in the P system or is it in a hybrid? And last but not least, I'm going to put the big if. Okay. So when we were talking about these ions and we were talking about the hetero, if it can go into an aromatic state, nature will pay the cost of a little bit of tweaking. All right. Hopefully that was informative. And what do we have to know about aromaticity? Resonance structures, what aromaticity is, how to predict it, and then just overall stability. All right. Until next time, jolly out.